Good morning. I'm Devisena. In this lecture, we are going to discuss about block diagram reduction techniques and rules for reducing the given block diagram. This topic is presented in the subject control system. Block diagram algebra. A block diagram is the diagrammatic representation of the flow of signals. It gives interrelationship which exists between various components. First, a functional block diagram is drawn to represent the functions of the system. Then it is converted into a mathematical block diagram by expressing the transfer function for each block. Finally, it is reduced to an equivalent simpler block diagram by its system analysis. We want to know the definition for the transfer function. The transfer function of a linear time invariant system is defined to be the ratio of Laplace transform of the output variable to the Laplace transform of the input variable under the assumption that all initial conditions are 0. This is the equation. That is, transfer function is equal to Laplace transform of output variable divided by Laplace transform of input variable. Need for block diagram reduction. Block diagrams of some of the systems turn out to be complex such that the evaluation of their performance required simplification or reduction of block diagrams, which is carried out by block diagram rearrangements. Advantages of block diagram. Very simple to construct the block diagram for complicated systems. Individual as well as overall performance of the system can be studied by using transfer functions shown in the block diagram. Overall closed loop transfer function can be easily calculated using block diagram rules. The function of the individual element can be visualized from the block diagram. Disadvantages of block diagram. Block diagram does not include any information about the physical construction of the system. Source of energy is generally not shown in the block diagram. So, block diagram for a given system is not unique. Basic components of block diagram. The basic components of block diagram are block, branches, summing point, arrows, and takeoff point. Block. It indicates the function of a particular system. R of S is the reference or controlling variable. G of S is the transfer function of the particular system. C of S is output or controlled variable. Here is a representation of a block. Here G of S is your block and R of S is the controlling variable or the input variable, and C of S is the output variable or controlled variable. This is represented here. Summing point. It is used to add or subtract one or more signals. Plus or minus indicates the add or subtract function. Plus symbol indicates the signal is added to the reference signal. It is called positive feedback. Minus indicates the signal is subtracted from the reference signal. It is called negative feedback. The signal which is added or subtracted to the reference signal is called feedback signal. This is a representation of a summing point. Here we are having a summer. To this, one input is your reference input R of S and the other input is your feedback signal, and plus or minus indicates that positive feedback or negative feedback that is applied to the summing point. This is the representation of a summing point. Takeoff point. Some of the signal at the top are bypass and it is given to other block for further performance. That is called as that point is referred to as takeoff point. Here the takeoff point is represented. The input-output behavior of a linear system is given by its transfer function. This is the representation for a block. R of s is the input, C of s is the output. The transfer function is represented as G of s is equal to C of s by R of s, where C of s is the Laplace transform of the output variable and R of s is Laplace transform of the input variable. General block diagram representation is shown below. This is the representation for a general block diagram. Here, input is supplied to the error detector as one input. The other input is from the feedback elements. That is, the feedback signal is applied to the error detector as other input. The output from the error detector is the error signal. This error signal is supplied to the controller. Then from the controller we are obtaining an actuating signal as an output. This actuating signal is applied to the plant and from the plant we are obtaining the output. In order to improve the performance of a system, we are taking a part of output that is considered to be a feedback. That feedback is supplied to the feedback elements. From that we are taking a feedback signal. This is represented here. Constructing block diagram for control systems. A control system can be represented diagrammatically by block diagram. The differential equations governing the system are used to construct the block diagram. By taking Laplace transform, the differential equations are converted to algebraic equations. The equations will have variables and constants. From the working knowledge of the system, the input and output variables are identified and the block diagram for each equation can be drawn. Each equation gives one section of block diagram. The output of one section will be input for another section. The various sections are interconnected to obtain the overall block diagram of the system. The general block diagram. Here, R of s is the reference or controlling variable. C of s is the output or controlled variable. E of s is the error actuating signal. B of s is the feedback signal. H of s is the feedback element. And G of s is the transfer function for the system. This is represented in this diagram. Forward transfer function G of s. It is the ratio of output signal C of s to the actuating signal E of s. That is, G of s is equal to C of s by E of s. Feedback transfer function H of s. It is the ratio of feedback signal B of s to actuating error signal E of s. Overall transfer function or closed loop transfer function. It is the ratio of output signal C of s to the reference signal R of s. That is, M of s is equal to C of s by R of s. This is the closed loop transfer function. Block diagram for a canonical system. Here is a general representation of a general block diagram. From this, G of s is equal to C of s by E of s. The closed loop transfer function is C of s by R of s. Therefore, C of s is equal to G of s into E of s. Consider this is equation 1. Now consider a negative feedback signal is applied to this. The actuating signal E of s is equal to R of s minus B of s. Consider this as equation 2. Feedback signal C of s into H of s is equal to B of s. Consider this as equation 3. Put equation 3 in equation 2. We get E of s is equal to R of s minus C of s into H of s. Consider this is equation 4. Put equation 4 in equation 1. Therefore, C of s is equal to G of s open bracket R of s minus C of s into H of s close the bracket. Consider this as equation 5. Rearranging equation 5, we get C of s open bracket 1 plus G of s H of s close the bracket, that is equal to G of s into R of s. Consider this as equation 6. That is, we have got the value of C of s that is available in this LHS side to the RHS side from the equation 5. So equation 5 becomes C of s into 1 plus G of s H of s, that is equal to G of s into R of s. The transfer function for the negative feedback signal is C of s by R of s is equal to G of s divided by 1 plus G of s H of s. The transfer function for the positive feedback signal is equal to C of s by R of s is equal to G of s divided by 1 minus G of s H of s. Rules for reduction of block diagram. Rule number 1. If the blocks are in cascade, then this is the representation of two blocks G1 and G2 which are in cascade. This is equivalent to, here is the representation. When two blocks are in series or cascade connection, then the resultant block is the product of the two individual block gains. Rule number 2. If the blocks are in parallel, then the blocks are added or subtracted depending on the summing point signal. Here is a representation of two blocks G1 and G2. These two blocks are in parallel. The signal from the block G1 and block G2 is applied to the summing point. This represented in this diagram. This is equivalent to the summation of the two blocks G1 plus or minus G2 depending on the signal that is applied to the summing point. The blocks output may be added. Here we have a positive signal, that is why the two blocks are summed up. When two blocks are in parallel, then the input signal applied to the two blocks are same and the output from the blocks are summed up by using summing point signal. Reduction of feedback loop. Original block diagram is shown below. This is the representation of a original block diagram, that is a general block diagram. If a negative feedback is applied to the circuit means then that C of s by R of s is equal to G of s divided by 1 plus G of s H of s. For positive feedback loop, the value of C of s by R of s is equal to G of s divided by 1 minus G of s H of s. The equivalent block diagram is shown below. This is the general representation of a block diagram after eliminating the feedback loop. Rule number 4. Moving the takeoff point ahead of the block, that is along the direction of signal flow. This is the representation. After shifting the takeoff point ahead of the block, the block diagram is equivalent to, here is a representation after shifting the block diagram from the input side towards the output side. We have included a block 1 by G. That is, if a takeoff point is moved ahead of the block, then divide the takeoff path by the contents of the block. Rule number 5. Moving the takeoff point behind the block, that is against the direction of flow. That is moving the takeoff point from the output side to the input side. The equivalent block diagram after shifting the takeoff point from the output side to the input side, we get, this is the representation. Initially, the takeoff point is present in the output side. Now we have shifted the takeoff point towards the input side. So we have included a block G at the takeoff point path. That is, when the takeoff point is moved against the direction of flow, that is behind a block, multiply the takeoff path with the contents of the block. Rule number 6. Moving a summing point ahead of a block, that is along the direction of the flow. This is the representation. Initially, the summing point is present in the input path. Now we are going to shift the summing point from the input side to the output side, that is along the direction of the flow. After shifting the summing point ahead of the block, the equivalent diagram is shown here. This is the representation of after shifting the summing point ahead of the block. That is, when moving a summing point ahead of block, that is along the direction of the flow, multiply the path of summing point with block contents. Rule number 7. Moving a summing point behind a block, that is against the direction of flow. That is, we are going to shift the summing point from the output side towards the input side. This is the representation. Initially, the summing point is present in the output side. We are going to shift this summing point towards the input side. The equivalent diagram after shifting the summing point from the output side to the input side, we get the representation like this. That is, when moving a summing point behind a block, that is against the direction of flow, divide the summing point path with block contents. This is indicated in the above diagram. Rule number 8. Interchanging two summing points. The original block diagram is shown below. Here we are having a summing point 1 and a summing point 2. For the summing point 1, the signals R1 of s and R2 of s is applied. That is applied to the next summing point. So for the next summing point, the inputs applied are R1 of s minus R2 of s close bracket plus R3 of s. So the output is C of s is equal to R1 of s minus R2 of s plus R3 of s. If we are going to interchange these summing points, means the equivalent circuit diagram or equivalent block diagram is shown here. This is the representation of interchanging two summing points. That is, the operation can be done without any modification except that the various signals are to be rewritten. Rule number 9. Moving a takeoff point ahead of a summing point. Original block diagram is shown below. Here, the takeoff point is present at the output side, and we are going to shift the takeoff point ahead of a summing point. So, the equivalent block diagram is shown below. This is the representation. Now, we are going to shift the takeoff point towards the input side. This is represented here. Rule number 10. Moving a takeoff point beyond a summing point. The original block diagram is here. Initially, the takeoff point is present in the input side, and we are going to shift the takeoff point towards the output side, that is beyond the summing point. The equivalent block diagram is shown here. After shifting the takeoff point beyond the summing point, the equivalent block diagram is represented here. Rule number 11. Expansion of summing points. Block diagram is shown here. Here, in this summing point, the signals A, B, C and D are available. The equivalent block diagram is shown here. Here, we have rearranged the signals. That is, one summing point is expanded to 2. The signals A and B are applied to summing point 1. We get A plus B signal. This A plus B signal is applied to second summing point. Already in the second summing point, the signal C is available. Therefore, the output from the second summing point is D. Its value is A plus B plus C. Here. Thank you very much for listening this lecture. For further updates, kindly subscribe this channel. If you like this video, means you can share this video to your friends.